All right, this set of notes is going to focus on writing decay equations, both for natural and artificial transmutation. So transmutation we talked about before when you have one element that transmutes into a new element. We're going to first focus on natural transmutation. You'll notice that it always starts with one nuclei or nucleus on the left-hand side, and then it's going to give off a particle and change into a new element. We'll look at the end at artificial transmutation, where we'll have a particle and it has to combine with another particle in order to transmute into a new element. So we'll be going over the two towards the end. We're going to start off with just some basics. One little thing is just remember that when we have the atomic notation, we have the element symbol, which is represented by E here. The top left is going to be your mass number, and then the bottom left is going to be your atomic number. And just remember that it's that atomic number that determines your element. So when we write decay equations, we're going to be balancing the charge and the mass. So the sum of the atomic numbers, or the charges, on the left, which are the bottom numbers, must equal the sum of the atomic number and charges on the right. And the same thing for mass numbers. Those top sum of the mass numbers on the left must equal the sum of the mass numbers on the top right. So that's what you'll see us doing as we go through all these different examples. So this is one completed natural transmutation. Uranium gives off an alpha particle to change into thorium. So the top numbers are your masses. On each side of the arrow, they have to equal the same sum. So 234 plus 4, which are these two top numbers, does in fact equal 238, so that is balanced. The charge, which are those atomic numbers on the bottom, also have to be balanced on each side of the arrow. So 90 plus 2 gives you 92, which balances out with the 92 we started with. So that is all set as well. So that's what you're going to see us doing in order to complete the different decay equations. So when we write these natural decay equations, you're going to see we only have one reactant to the left of the arrow. We're going to refer to table N to figure out, does it give off an alpha, beta, or positron, and then we'll go from there to figure out what it transmutes into. So our first example is the alpha decay of plutonium-239. So I'm going to start with plutonium-239. So I use the symbol, the mass number, and then you usually have to look up on your periodic table the atomic number of 94. You want to make sure you have all three pieces there whenever you go through this. I'm telling you that it's going to undergo alpha decay. You would also find that on table N. So I'm going to first write the notation using table O to get the alpha particle. Now think of the arrow as your equal sign. So 4 plus an unknown has to equal 239, which means I need a 235 in the top part. 2 plus my bottom number has to equal 94. So that means the bottom number has to be 92. So first it's just a matter of dealing with the math. Then I'm going to look at the 92, and that's going to determine my symbol. Always make sure if you change the bottom number, you have to be changing the element symbol. That's probably the biggest mistake students make. So element 92 is uranium, so a capital U. Cobalt-60 undergoes beta decay, which is probably the trickiest one for students. So you have cobalt-60, so I would look up the atomic number 27, plug in the mass number that they gave me. I'm going to first include the beta particle, which has a 0 and a -1 on the bottom. So when I go to calculate the mass number of my new element, I'm going to have 0 plus x is equal to 60, so I know I need a 60 on the top. And then be super careful here. What plus -1 is going to give you 27? You would have to actually need a 28 here in order for the math to work out. So 28 plus a -1 is 27, which balances out the 27 of the cobalt. And then always, again, double check the periodic table. Atomic number 28 gives you the symbol nickel, or Ni. So again, if that bottom number changes, you're undergoing transmutation, so you need a new element. And then finally, an example of your positron decay. We're going to use iron 53. So we have iron has atomic number of 26, and then we plug in the same mass number that they give you in the problem. A positron is going to be a 0 with a +1 on the bottom. So when we do the math, 0 plus 53 equals 53 from the left, and then 1 plus 25 equals 26 on the left. Using that 25 and looking it up on the periodic table, I get Mn, so manganese. So this would be a good spot for you to pause the video and actually try a couple of these out. I put table N on the bottom there. You just need your periodic table to look up atomic numbers. So at any point pause, I'm going to show you at least the first step in terms of setting this up. So the first step you want to do is actually get down the radioisotopes, making sure you include their atomic number. And then I use table N here to fill in if it went through alpha, positron, or beta decay. And you can see that right down here on table N. So this would be a good spot if you at least got here to see if you can come up with the new elements they transmute into, and then you can check it. And when you check it, you should get the same answers as I have here. And again, you'll see all the masses and charges are always conserved, always balanced, which is how I'm coming up with these new elements, what they transmuted into. And we'll be practicing this quite a bit tomorrow. You've already seen some of it with the activities we've done in class. Finally, I just want to show you some examples of artificial transmutation. So this is when scientists can force one element to change into another by bombarding it with high energy particles. So usually particle accelerators can be used here. The same basis of balancing atomic numbers or charges and their mass numbers, they have to be balanced on both sides. So if we have carbon-14 isotope that forms when an atmospheric nitrogen is bombarded by a neutron. So we have the nitrogen, and it's going to get hit by a neutron and transmute into carbon, and they want to know what this missing particle is. So we're going to use the same math of just that arrow has to be an equal sign for each side. So for the top number, I would have 14 plus 1, that's just these numbers right on top, is equal to 14 plus x. So I now know the top number is a 1. On the bottom, 7 plus 0 is going to equal 6 plus, I put y there, it's just a different variable, will give me 1. Then I'm going to either, again, use the atomic number, or I can just look it up on table O in this case to get the 1 over 1. Either way, I'm going to see that it's a hydrogen. And then on the very bottom here, we're going to again fill in the missing particle by balancing out and conserving mass and charge. So in the top, I would have x, my unknown, plus 4 is equal to 1 plus 30. So that's going to give me a mass of 27 to balance that. And then on the bottom, I'm going to have y plus 2 is equal to 0 plus 15. So that gives me an atomic number of 13. And then I use that 13 and the periodic table. And aluminum has the atomic number of 13. So again, just that idea of balancing out and conserving mass and charge here is how you're going to solve these. And also utilizing your periodic table. So one little quick check-in, you need to be able to differentiate between natural and artificial transmutation. So in this one over at number 1, which one represents natural transmutation, right off the bat you can get rid of C and D. Those are regular chemical equations, and we're looking for transmutation. So for natural, you're always going to pick the one that just has 1 on the left. A would be an example of artificial here because you have 2 on the left. So B would be natural transmutation. And then over here, artificial, A is the only one that has that atomic notation in the equation. B, C, and D are all examples of chemical equations. The other thing is that with the atomic notation, you have the 2 things on the left, which is an indication that you have artificial. So best choice there is A. All right, we're going to practice a lot with decay equations in class, and make sure you get the hang of this.